Finally, let's talk about tangent planes. Our goal is to find equations of tangent planes. So for a point on a surface, we would like to find the equation of the tangent plane to that surface. We know the answer for graphs. If our surface happens to be a graph z equals f of xy, then we know how to find a tangent plane equation. We would just use the local linearization z equals L of xy. And we know the normal vector to that was partial f partial x, partial f partial y, minus 1. But what about other surfaces? And an important case to consider is level surfaces. We met these briefly before. Here's a reminder. We have a function f of x, y, z, and we set it equal to k. The set of points where f of x, y, z comes out equal to k is a level surface of f, because it's a whole surface where f has level values. For example, if f of x, y, z was x squared plus y squared plus z squared, well, if we set that equal to 1, 4, or 9, we would get these spheres. And you saw this graphic as well. This time the function is the function x squared plus y squared minus z squared, and setting it to different constants gives us different surfaces. So for surfaces like this, could we find the equations of the tangent planes? Before we get into the tangent planes themselves, a question for you about level surfaces. F of xyz is the function 3x plus 4y plus 5z. And what are the level surfaces of that? Are they parallel planes, intersecting planes, nested spheres, or more than one of the above? What do you think? Pause the video and think about it. The answer is A. They are parallel planes. So 3x plus 4y plus 5z equals a constant. That gives you a plane with normal vector 3, 4, 5. They all have the same normal vector, so they're all parallel planes. So you get these sort of stacked up parallel planes that all have the same normal vector. All right. Now we're ready to figure out tangent planes to level surfaces. So let's take a surface defined by one of these equations, f of xyz equals k, and a point on S. And we're going to put this requirement that at that point our function has to be differentiable. It has to have derivatives, and the gradient can't be 0. If all the derivatives are 0, then that would be a singular point of surface S, like a corner or a cusp or something like that. And at a corner, it's a little hard to say what you mean when you say tangent plane. So we're just going to rule that out. It's a little bit of a technicality, maybe, or it feels like a little bit of a technicality, but we're not going to talk about corner points. Just not going to deal with that. So as long as we're not at a corner point, then what is the tangent plane to that surface at that point? We know one thing. We know that the tangent plane passes through that point P. The only other thing we need is we need a normal vector to the plane. Well, the answer is that the gradient vector is a normal vector to the tangent plane. The gradient vector. Once again, gradient vectors are showing up. The first useful fact about gradient vectors was the relationship with derivatives in different directions, and that got tied in with the rate of change along a path. And now we're doing another new connection, which is that the gradient vectors give us the normal vectors to the tangent plane. Oh, there's one other stop along the way, the direction of steepest ascent, the steepest uphill direction. Yeah, that was another cool thing about gradient vectors. Okay, so this is what, the fourth thing, depending how you count it. Yeah, that sounds about right. So being a normal vector to the tangent plane. And at that point, we have all the information we need. We have a normal vector to the tangent plane, and we know a point that the tangent plane passes through. So those two pieces of information are enough to write down an equation. Here's a picture, just to illustrate what we've been talking about. So here's a level surface. This is a surface x squared minus y squared plus z squared equals a negative number. It's from this example. Oh, I said it backwards. It's a positive number. This is x squared plus y squared minus z squared equals a positive number. Oh, well. Oh, sorry about that. Anyway, so this is a level surface of that function, and at that point the tangent plane sort of just touches at that point. What they've drawn here is a normal vector, which is the gradient of the function f. F is the function x squared plus y squared minus z squared. So do you think you could figure out the gradient? Hopefully you thought of 2x, 2y minus 2z. And if you did, good job. That vector is a normal vector for the plane. Why is the gradient a normal vector to that tangent plane? Well, I'll show you. It's kind of fun. Let's take any curve r of t on the surface S. So it can wiggle around, and it goes through the point P. So let me go back to the previous slide. It could be, it could go around this cylinder, and then it goes through P, say. Then the idea is to look at the function f of r of t. Well, r of t is in S, means that f of r of t is k, right? Everything on S has f of it equals k, and these are points in S, so f of them equals k, and that's constant. So that means that if I took the derivative of f of r of t, we would get 0. But that is a derivative along a path, or a rate of change along a path, which we talked about before. So it's a chance to use that rate of change along a path that we developed. The rate of change along the path is the gradient of f at that point, taking the dot product with r prime of t. And that comes out to be 0. So that means that the gradient of f is perpendicular to r prime of t. Well, going back to the picture, right here, there's r prime of t. And look at it, it's a tangent vector to that curve. That means that it's a tangent vector to the surface. So this r prime of t is a tangent vector in the tangent plane. And this is going to work for any curve. So this is actually any tangent vector. And that's telling us that the gradient vector of f is perpendicular to the whole tangent plane. That's how we know that gradient of f is a normal vector. Okay, so we've finished saying a proof. I hope that was fun to hear. I hope you enjoyed hearing how we were able to use our knowledge about rate of change along a path, which is fresh, right? That was just earlier in this same section, and the connections between curves, surfaces, and tangent vectors. So I hope that was fun to hear. I'll say that on a practical level, we're not going to ask you to come up with proofs like this, but the conceptual understanding might be helpful to what you're learning. Another figure. This time it's a two-dimensional figure. There's just an f of x, y. So instead of level surfaces, these are level curves. These are the points where f equals 40, the points where f equals 80, the points where f equals 120, and so on. So these are level curves. And what this figure is illustrating is that the gradient, the blue vector, gradient of f, is perpendicular to the level curve, and it's a perpendicular line for the tangent line. So the level curve is a curve, it has a tangent line, and the gradient of f is a perpendicular vector or normal vector for that tangent line. Just like in 3D, the gradient vector was a normal vector for the tangent plane. One other piece of information we have is that so this is the new information, being orthogonal to the level curve, and it's the same story as it's the same reason why as for the being orthogonal to the level surface. But the other piece of information that we actually had before is that the gradient points in the uphill or increasing direction. So based on that, here's a question for you. There's a contour diagram of a function f of xy. So notice that 1 is the innermost circle, then 2, then 3 is the next circle after that, and then 4, and so on. So the numbers are getting bigger as you go out. Okay, so out of the points A, B, C, and D, out of those 4 points and those 4 vectors, which one of them could be the gradient of f at its corresponding point? What do you think? Pause the video and think about it. The answer is B. B is the only one that could be the gradient vector. A, it points downhill. The gradient is supposed to point uphill. C and D, these are not perpendicular to their level curves. In fact, D is tangential, right? It has a 0-degree angle to its level curve, and C looks like it's at a 45-degree angle, or more or less, or at least that's what it looks like, about a 45-degree angle. They're not orthogonal. A is orthogonal to its level curve, so I got that right. And B is also orthogonal to its level curve, so little check mark for being orthogonal. But A is pointing downhill and B is pointing uphill. So B is the one that could be a gradient vector. Okay, so that brings us to the end of the section. Just to recap, because we covered quite a number of items here, we introduced the gradient and we said what it is. It's a vector whose entries are the partial derivatives of a function. We talked about derivative with respect to a vector and the directional derivative, and these are things that let you take a derivative in any direction, not just the x, y, or z axis directions, but it could be in between or diagonal directions. And we saw that derivative with respect to a vector basically just came down to doing a dot product with the gradient. We used that fact to figure out a chain rule for paths. Then we looked at the geometry of gradients, and we said that they point in the direction of steepest ascent of a function, meaning the direction with the maximum rate of increase in that direction. And finally, we saw how gradient vectors give normal vectors and equations for tangent planes of level surfaces. Okay, thanks for watching. Bye.